In our last video, we took a look at being able to use the Lotka-Volterra equation to be able to find a predator-prey system for rabbits and wolves. And we ended up getting this system, the dx dt is equal to 0.08x minus 0.001xy, and dy dt negative 0.02y plus 0.00002xy. And eventually we found that the equilibrium points were 1,080, so 1,000 rabbits and 80 wolves. So now what we're going to do is we're going to find an expression for dy dx, and then we're going to interpret its meaning when x is equal to 6, x is equal to 20, and y is equal to 70. And then we're going to plot a direction field for this. All right, so first of all, one of the things to remember is that to find dy dx, we can just use an algebra trick and say, well, that's the same as dy dt divided by dx dt. Right? In other words, we just use a chain rule. Right? And what we could do is we could just pull down from our system immediately, because we know dy dt is negative 0.02y plus 0.00002xy. And in our denominator, dx dt is 0.08x plus minus, excuse me, that negative 0.001xy. All right, so that's our expression, really easy. And of course, what we're going to do is we're going to substitute x is 20 and y is 70, and we're going to figure out what that means. So dy dx at the point 20, 70 is going to be equal to negative 0.02 times 70 plus 0.00002, 20 times 70. And then we're going to divide all of that by 0.08 times 20, and then minus 0.001 times 20 times 70. All right, and we're just going to shove that in our calculator. So be patient with me as I put this in the calculator. So we have negative 0.00 or 02, I think it was. So real quickly, we have to go back and forth. So 02y, and remember y was 70, plus 4 zeros, 2, and then 20 times 70. All right, and that's just our numerator. So that's going to give us negative 1.372. Right. So I'm going to write that down. So we have negative 1.372 in our numerator, and then in our denominator, we have our 0.08 times 20, which was our x, and then minus, I can't remember, I think it was 0.0001, but let me verify that. So 0.0001. Yep. Or I think it was 001. Let me triple check just to make sure. I don't want to put the wrong thing in there. 001. Good. All right. So 001 times 70 times 20, or 20 times 70, doesn't matter. And so our denominator is going to be 0.2. All right. So, and then we can just take the negative 1.372 divided by 0.2, and we're going to end up with negative 6.86. All right. So going back here, we end up with our 0.2 in the denominator, and that's going to equal negative 6.86. Now, what does that mean? All right, well, remember dy dx is going to be the rate of change of, so we're going to say delta of the wolves. So it's the change in the wolves divided by the change in the rabbits. Okay, so what that means is we're basically saying that for every one less rabbit, or for every one more rabbit, we're going to lose um, basically about 7 wolves. All right, so what that means is that there's not enough rabbits to sustain the wolves. Okay, so if we increase 1 rabbit, we lose 7 wolves. Okay, and you might remember that the equilibrium was X was 1,000 and Y was 80. So we definitely need a lot more rabbits than wolves to sustain the population. All right, so it kind of makes sense that this sort of thing is going on here. Okay, so that's the real life interpretation of this. And of course, what this means also is at the point 2070, the slope of our direction field is going to be negative 6.86. And from there, what we can do is we can create something called a phase plane. That's part C. And if you really wanted to, you could just go by hand and just do a whole bunch of these if you wanted to. All right, but it's a little bit easier for us to be able to use the technology. So I'm going to show you how to use technology to get a phase plane and what we're specifically looking for. All right, so now to get to the phase plane, it's a little bit tricky. You're going to go to Wolfram Alpha, right? And you're going to have to look at their widgets. All right, there's not really a good phase plane operator just from Wolfram Alpha, so we're going to go to the widgets. All right. And you're going to click right here where it says Wolfram Alpha widgets. And then you're going to have to search their widgets. All right, so you're going to browse and then you're going to search. All right. You're going to find a widget, and you actually have to delete where it says find a widget and just type in phase plane. It looks like somebody already did that. I believe 2 are going to come up. All right, and just pick this first one. All right, they're both decent, but I picked the first one. All right, and what you're going to have to do is you're going to have to type in both the phase planes. All right, so the dy or equation 1. So this could be dy if you want to. So you can either type in dx dt or dy dt. So I'm just going to type in dx dt, or so that's 0.08. So remember, this is one of the original ones, minus 0.001 xy. And I'm going to say times x times y. And here I forgot my x. And then down here, negative 0.02 y plus 0.12342 times x times y. All right. Now the interval is important as well. All right. So I'm going to graph this first just to show you what's going on. All right. And this is the phase plane. They call it a stream plot, but it's just called the phase plane. And I want you to notice it's 0, 0. It's kind of like that equilibrium point going on. Okay, so it's kind of a special one. If we were to zoom in a little bit more, so let's say I do negative 1, comma 1, and then 1, 1, and submit it. So I'm just changing the view of this. All right, we clearly see that this is almost like a point. It's not a sink, all right, but it's actually kind of a repulsion point. Okay, so everything is kind of stemming from the 0, 0 point. Now let's take a look around the point. Remember, we had another point when x was 1,000. So let's try something like 990, comma 1010, and then remember that 80 was the other point. So I'm just going to look at this point, and I'm going to submit. All right, and again, we get kind of like around this point where 1,080 occurs. We start getting like this sort of divergent behavior. All right, so we can see like the arrows go left, the arrows go right, the slope's almost 0, which you can notice from each of the arrows, which is really cool, right? Because remember we said that the closer we get to 1,000, 80, the closer the equilibrium is. All right, so that basically means there's going to be very little change. All right, If I zoomed out just a little and did something like 900, comma 1100, and then let's just say 0 to 200. All right, just a little bit bigger scale, and submit it. All right, then we get this. All right, and we can kind of see like right here, like right around that point, 1000 comma 80, that we get like this divergent sort of behavior. It's almost like it's circling around there. All right. Now this is a pretty rudimentary phase plane plotter, and it helps you to be able to get a gist of what's going on. But it's not a really good one like MATLAB or Mathematica would plot one. So I did plot one in Mathematica that I'm going to share with you just to show you what it looks like. All right, if you were to be able to program it. And this is what I got when I plotted it in Mathematica. So here's our phase plane, and you can notice right around the point 1000 comma 80, there's like this sink, if you would, like a hole. Okay, that's what a lot of these Lotka-Volterra equations do, is that they produce like this circular sort of behavior right around the equilibrium point. All right, so pretty cool that you can actually see the equilibrium point. All right, so right here, right in the middle here, this is our equilibrium point of, we said 1000 comma 80. All right, so you might be able to guess the solution, all right, if you have a pretty good phase plane grapher without actually finding the equilibrium points. Okay, so that's pretty cool. All right, so we're going to move on and we're going to take a look at one last application of systems. So we're going to start taking a look at fluid flow beyond or among different tanks.